Imagine you're facing something really frightening, like a potential Alzheimer's diagnosis or maybe a brain tumor. And then you have this agonizing wait, sometimes weeks, maybe even months, just for a clear answer.
That uncertainty, it's a reality for millions. It's just awful. The WHO estimates, over 3 billion people have some kind of brain disorder. So getting that early, accurate diagnosis, it's not just important, it's potentially life-saving or life-changing.
Absolutely. And we have these amazing tools now, like MRI, magnetic resonance imaging. But the bottleneck seems to be the analysis, right? Doctors manually looking through these complex scans.
Exactly. It's incredibly time-consuming. And, it's prone to human error, which is understandable given the complexity. It just slows everything down. Getting patients the answers they need, it's an efficiency issue, but also an accuracy one, too.
So that brings us to our deep dive today. We're looking at something pretty exciting, a new approach called DGG-XNet. It's a hybrid deep learning model, and the idea is to tackle these diagnostic hurdles head-on.
Right. Making it faster, more accurate.
And crucially, more transparent. We're talking about potentially bringing real clarity to these super complex medical images. Could, really change the game for diagnosis.
It really could be pivotal, especially when you think about the human side of things. Take Alzheimer's. The way it progresses is just heartbreaking. Starts often subtly, memory loss, then maybe difficulty recognizing people, places they know well. And in the later stages, it can affect the most basic things, eating, breathing.
This is devastating.
It is. And globally, the numbers are staggering, like 246 million affected, maybe 39 million in really critical condition.
And diagnosing it is so tough, isn't it? Because those early symptoms, they can look like other things.
Exactly. Like vascular dementia, the symptoms can overlap quite a bit.
It's like finding a needle in several haystacks that all look the same.
Yeah.
Getting that accurate diagnosis early is just paramount.
Couldn't agree more. And then you have brain tumors, another huge challenge. They can pop up sometimes from existing vein or nerve issues, and the consequences, partial or even complete sight loss sometimes. And there are factors linked to them, to severe myopia, genetics, even poor blood circulation seems to play a role sometimes. So the danger is real, and it just highlights this urgent need for, faster, automated ways to catch these things early.
So looping back MRI is incredible technology, but that manual interpretation, that's the real slowdown. That's the bottleneck.
That's it. The future really seems to point towards boosting these computational tools. We need more speed, more precision.
Which is where DGG-XNet comes in.
Right.
You mentioned it's hybrid. Why hybrid? Why not just use one really powerful AI model?
That's a great question. So we have things called convolutional neural networks, CNNs. They're fantastic for image classification tasks, really powerful. But the catch is a single CNN design often struggles to be universally brilliant across all types of neurological disorders. They each have slightly different visual clues.
Okay, so one size doesn't fit all.
Pretty much. So the idea of a hybrid model, one that combines the strengths of different approaches, becomes really appealing.
Right. So DGG-XNet isn't just one thing, it's a team effort. What's in the team? What are the components?
It cleverly merges two well-known networks, VGG16 and DenseNet121.
Okay. VGG16, what does that bring to the party?
Think of VGG16 as being really good at understanding the structure, the spatial layout of an image. It builds up these strong hierarchical spatial representations. So it's great at seeing the bigger picture, the key shapes and forms in medical images, like changes in tissue. Very robust for that.
Okay. Hierarchical spatial gets the structure. What about DenseNet121? What's its special skill?
DenseNet121 is designed for efficiency. It promotes something called feature reuse and efficient gradient flow through dense connectivity.
Dense connectivity. Sounds intense.
Well, maybe think of it like this. Imagine a team of detectives where every time one finds a clue, they instantly share it with everyone else on the team, not just passing it down the line.
Ah, okay. So information spreads much faster and more widely.
Exactly. That's the dense connectivity. It helps the network learn more deeply and efficiently from the data because features discovered early on are easily accessible later.
So DGG-XNet combines VGG16's knack for structure with DenseNet121's efficient information sharing. It gets the best of both worlds.
That's the core idea. You harness these unique characteristic extractions, as the researchers put it, to boost the efficiency for classifying multiple things, tumors, Alzheimer's, or normal brains. The goal was an efficient, quick detection model.
Makes sense. So how did they actually, build and train this DGG-XNet? What data did they use?
Good question. They started with a combined data set, Part of it came from the BraTS 2021 Task 1 challenge that provides MRI volumes for brain tumor classification. And the other part was an Alzheimer's dataset 4 class of images they found on Kaggle, which has 2D brain images for Alzheimer's detection.
Okay, so specialized data for tumors and Alzheimer's. How did they prepare all that data for the model? Must have been quite a job.
It's a critical step, data preparation. First, they standardized everything. All images resized to 224 by 224 pixels and normalized. That consistency is key for the AI. From the BraTS data, they focus specifically on the T1-weighted MRI scans.
Why T1 weighted?
T1 scans are really good for showing the anatomy, the structure, distinguishing different tissue types in the brain. Very useful here. They also took the 3D MRI volumes and extracted evenly spaced 2D slices, like pages from a book.
Right.
And here's a really clever bit. They equalized the dataset using downsampling.
Downsampling.
They looked at the number of images they had for each class tumor, Alzheimer's, normal. If one class had way more images, they randomly removed some from that larger class until all classes had the same number of samples. In this case, they ended up with 500 samples per class.
Ah, I see. So the model doesn't just get really good at spotting the most common condition because it saw more examples of it.
Precisely. It prevents bias, ensures the model learns equally well across all conditions, super important for fair and accurate diagnosis.
Okay, data prepped and balanced. What about the actual training process? How did they teach the model?
They split the data carefully. 70% for training the model initially, 20% for validation, sort of like practice tests to fine-tune it, and 10% held completely separate for the final exam, the testing phase. And they used stratified sampling for this split.
Stratified meaning it keeps the balance.
Exactly. It makes sure that 7/20/2010 split maintains the same proportion of tumor, Alzheimer's, and normal images in each set. Keeps everything fair. They also use a technique called transfer learning.
Right. Using knowledge from elsewhere.
Yeah, like giving the model a head start. They initialized it with weights pre-trained on ImageNet, a huge database of everyday objects. Then they fine-tuned it for the medical images. Initially, they froze some layers, let the model adapt slowly. For the learning itself, they used the Atom optimizer. Think of it as a smart way to adjust the model's parameters with a specific learning rate, and categorical cross-entropy as the loss function.
Loss function tells it how wrong it is.
Essentially, yes. It measures the difference between the model's prediction and the actual truth, guiding it to get better. And one more key thing, early stopping. This watches the performance on that validation set. If the model doesn't improve for, say, 5 learning cycles, it stops the training.
Why stop early?
To prevent overfitting. That's where the model gets too good at the training data, memorizes it almost, but then fails when it sees new, unseen data. Early stopping helps find that sweet spot, and it restores the best performing version of the model it found during training.
Very clever. Okay, so after all that careful training, what does the model actually output? What does it tell the user?
Simple and clear. It classifies the input brain scan into one of 3 categories: tumor, normal, or Alzheimer's.
Right, the moment of truth then. How well did DGG-XNet actually do on that final test set? What were the results?
Okay, get ready for this. The headline number is pretty impressive. 91.33% accuracy on the test set.
Wow, 91%. That's really high for this kind of complex task.
It is. And what makes it even more compelling is how it stacks up against other well-known deep learning models when tested on the same data. For instance, VGG16 on its own, 84.67%. DenseNet121 by itself, 82.67%.
So the components alone were significantly lower.
Yes, exactly. And others like Inception B3, MobileNet B2, ResNet 50, they were all in the range of like 78% to 82%.
Okay.
Even really deep networks like ResNet 101 only hit 68%, and EfficientNet B3 was around 74%. So DGG-XNet really stood out.
That is a significant jump, 91% compared to mid-80s or even lower. Was it just accurate overall, or was it consistent across the different types, tumor, normal, Alzheimer's?
That's a key point. It wasn't just high accuracy, it was robust across the board. Its precision, recall, and F1 scores, these are other important metrics, were all above 91%. The macro average F1 score, which balances performance across all classes, was 90.00%.
Okay.
Plus, it had high AUC scores, that's area under the curve, basically measuring how well it distinguishes between classes, and the confusion matrix showed very few misclassifications. So yes, very consistent performance.
So what's the magic ingredient then? Why did this hybrid approach work so much better than the individual models or other established architectures?
Well, it really seems to come down to that synergy you mentioned earlier. Combining VGG16's strength and spatial understanding with DenseNet121's efficient feature sharing, It creates something more powerful than the sum of its parts for this task. Plus, those meticulous steps, the transfer learning, giving it a good start, the careful fine-tuning, the crucial data balancing to avoid bias, and using early stopping to prevent overfitting. It's really a combination of smart architecture and smart training strategy.
It really highlights how designing the AI, not just throwing data at it, is key.
Absolutely. Architectural collaboration, you could call it.
Now, this brings us to something really vital, especially for doctors actually using this. AI models can be powerful, but often they're like black boxes, right? They give an answer, but it's hard to know why.
The black box problem. It's a major hurdle for trust and adoption in medicine. If a doctor can't understand how the AI reached a conclusion, they're understandably hesitant to rely on it for critical decisions.
So how does DGG-XNet tackle this? Does it offer any explanations?
Yes, and this is crucial. The researchers used explainable AI, or XAI techniques, specifically things like Grad-CAM and Integrated Gradients.
Grad-CAM, what does that do?
Grad-CAM essentially creates a heat map overlay on the input image. It highlights the regions of the scan that were most important, most influential in the model's decision-making process. So you can visually see, the model was really focusing on this area when it decided tumor. It gives you a sort of coarse localization.
Okay, so it points to the important neighborhood. What about integrated gradients? Sounds more detailed.
It is. Integrated gradients goes deeper down to the pixel level. It attributes the prediction score back to individual input features, basically, individual pixels. It helps understand which specific details in the image contributed most strongly to the final classification. It's much more granular.
So putting these together, Grad-CAM shows the where, and integrated gradients gets more into the what specific features mattered.
That's a good way to think about it. The combined effect is a big boost in interpretability and transparency.
Which makes the model much more trustworthy for doctors, right?
Yeah.
They're not just getting an answer, they're getting some insight into the AI's reasoning.
Exactly. It shifts it from being a potential oracle to being more like a diagnostic assistant, one that can show its work. That's huge for clinical applications.
It really feels like a necessary step for AI in medicine.
Fundamental, I'd say. It builds trust and facilitates that human-AI collaboration.
So wrapping this up, what's the big picture takeaway from this DGG-XNet research?
I think this deep dive really shows DGG-XNet's potential as a really effective but also interpretable tool for computer-aided diagnosis, both for neurodegenerative diseases like Alzheimer's and for brain tumors. It's a clear step forward.
Definitely feels like it. And it leaves us with a fascinating thought, doesn't it, for you listening? If AI like this can not only diagnose with high accuracy, but also explain its reasoning, show its work, how might that change the future role of doctors? Could it free them up from some of the more tedious diagnostic analysis to focus more on, say, the patient interaction, the human connection, complex treatment planning? And where else could this kind of explainable AI make a difference? What other medical fields desperately need tools that don't just give an answer, but explain how they got there?
It's a powerful question, and the researchers themselves are already looking ahead. They mentioned future work like incorporating full 3D volumetric analysis, not just 2D slices.
Even more data.
Right. And maybe adding other MRI modalities, not just T1-weighted scans. Plus, exploring things like data augmentation and domain adaptation to make the model even more robust across different hospitals, different scanners.
So the journey's definitely not over.
Not at all. The potential for this kind of transparent, effective AI to really transform diagnostics seems immense. It's a very exciting space to watch.